Well, hello, ladies and gentlemen. We're going to move on from chapter 5, which is the second law of thermodynamics. And we're going to move on to concretizing the second law in the most thoroughly rigorous and mathematical way possible, so that we can start using the second law automatically and in a mathematically rigorous way to solve problems. Remember all those pictures that we had, the Clausius inequality, the Kelvin-Planck statement of the the Clausius statement, the Kelvin-Planck statement of the second law. Those pictures are gone. We have the Clausius inequality, which we derived last time. It's an inequality, which is a bit of a pain, but it's still a mathematical representation of the second law. But we're going to improve on that today. We're going to improve on the Clausius inequality by deriving, or at least justifying, the existence of a new property, entropy, symbolized by the letter S. So we're going to move on to entropy today. In particular, we're going to develop the closed system entropy balance, do a little derivation today, derive the entropy balance for our property S, or entropy. This entropy balance is going to be a little bit strange looking, stranger than the energy balance, less intuitive. So we're going to spend a little bit of time talking about how to interpret each term in the entropy balance. We'll then move on to various versions of the entropy balance for a closed system. The overall process, rate-based, differential, or infinitesimal process, just like for the energy balance. The entropy balance has different versions which are more or less helpful to solve certain kinds of problems. Then we're going to look at how to interpret this new term. I told you the entropy balance is going to look a little bit strange. It's going to look strange. One of the reasons it's going to look strange is because you have this entropy source term. Entropy can be generated due to irreversibilities within the system. Remember the second law about reversible versus irreversible processes? Well, the presence of irreversibilities within the system during the process results in entropy S being generated. Entropy is not conserved like energy. It can be generated. So we have this S-gen term. S-gen or S-generated, which we'll investigate. How is S generated? Where is it generated? We'll talk about that when the time comes. And then we'll try to make concretize the entropy balance for a closed system by doing a very simple problem to get you started. We'll do heat transfer from hot to cold through a wall. So we have a plain wall. Heat flows from left to right, from the hot side to the cold side of the wall. We're going to do an entropy balance on the inside of the wall. We'll talk about how to interpret the results, okay? Okay, so let's get started here. Let's get started. What's this thing entropy about? Well, the first thing I'm going to do is I'm going to write the Clausius inequality. I'm going to write the Clausius inequality right here. So recall, over a cycle, the differential amount of heat transfer divided by the temperature at which the heat transfer occurs has got to be equal to the following. If the cycle is reversible, the cyclic integral is 0. Reversible cycle. So that integral is 0 when it's a reversible cycle composed of reversible processes. And it is less than 0 when there are irreversible processes within the cycle, or irreversibilities. So that cyclic integral can take on two values, either 0 or something negative, depending on the process. All right? Now, let's look at a system. Let's look at a system that moves from state 1 to state 2 and back to state one. So it undergoes a cycle. Undergoes a cycle. All right? Let me show you what the cycle might look like. So here's state one. Here's state two. And we're back to state one again. Okay? Now I'm going to put a hard constraint and a soft constraint on this cycle. A hard constraint is process 2 to 3 is going to be reversible. That's going to be my hard constraint. 2 to 1. Did I say 2 to 3? 2 to 1, reversible. 2 to 1 is reversible. I'm going to put that constraint on my process. And I'm going to put a soft constraint, which means in a moment I'm going to relax it. I'm going to say 1 to 2 is also reversible. So I'm just going to write reversible right next to process 1 to 2. Okay? So this is a hard constraint from 2 to 1. So I'm going to put some explanation points here. And 1 to 2 for the moment is reversible. Okay? So let's write the Clausius inequality here. Okay? Now I'm going to break up this inequality, the Clausius integral. Sorry, I'm going to write the Clausius integral. Let's break it up into process 1 to 2 and 2 to 1. So this is the integral of del Q over T from 1 to 2. Plus the integral of del Q over T to back to 1. All right? Now this, I'm going to say that this path here, 2 to 1, is not only reversible, but the path is fixed and reversible. I'm going to put some blue chalk here. So not only is it reversible, but it is a fixed path. So I'm going to write here 2 to 1 reversible, and then I'm also going to write fixed. Put explanation points right there, fixed. So 2 back to 1 is fixed. That means this integral right here, 2 to 1 is fixed. Why? Because the path 2 to 1 is fixed. So this guy is fixed. All right, the second integral is fixed. Now, I've also said for the moment that both of these processes are reversible. So I'm going to put brackets around the del Q over T. And I'm going to write reversible, R-E-V, reversible, reversible, indicating that those are evaluated over a reversible process. All right? Okay, so if these are both reversible processes and the cycle is reversible, then the Clausius inequality says that this cyclic integral must be equal to 0. Okay? So that implies I'm going to take the del Q over T from state 1 to state 2 over on the other side of the equation. I'm going to flip the whole equation. So this implies that the integral from state 1 to state 2 of del Q over T, and remember process 1 to 2 for right now is reversible. Reversible, R-E-V, is equal to minus the integral of del Q over T, and this is also a reversible process, from state 2 to 1. And remember, this is fixed. Why? Because process 2 to 1 is a fixed process, and it's reversible. Okay, let's think about this for a minute. Let's say I vary process 1 to 2. 2 to 1 is fixed, but 1 to 2 is not necessarily fixed. I can go from state 1 to state 2 along any path I want. Let's say I go along a new path. Okay, a new path. Oops, gotta come back. There we go. Which is also a reversible path. So let's say both of these are reversible. So I can vary the path here. Vary path. So the left integral is evaluated over a variable path that can change. And the right side integral is fixed because I fixed the path. What this is saying is this integral, del q over t from state 1 to state 2, is invariant. It has the same value for any path required or provided that path is reversible. This is fixed, so that means this is fixed. This integral has the same value no matter what the path is. No matter what the path is, it has the same value provided that path is reversible. So this strongly suggests that there exists some kind of property or point function. Property or point function called S, of which the change is equal to this integral over a reversible path. This is path independent. It basically means that this thing represents the change in a property. Okay? So let me write what I have here. I'm going to write it over here in the corner, and we're going to play with it. So let me write down, oops. Let me write down what I have written over on the other side. We're going to play with it. Let's take what's important and see where it takes us. So I've hypothesized a new property, S. S equals entropy of which delta S from 1 to 2 is equal to the integral of del Q over T for a reversible, or I'll just put REV, for a reversible process. Delta S from 1 to 2 is equal to del Q over T for a reversible process. That's what we concluded by having a fixed and then a variable path and evaluating the cyclic integral del Q over T over the cycle. And we utilize, of course, the Clausius inequality, which says that that cyclic integral is 0 if it's a reversible cycle. All right? Okay, let me draw our system path one more time. Okay, so I have 1, 2, back to 1. And I've said here that the process 2 to 1 is reversible and fixed. That's our blue one, as I recall, blue and white. Okay. And remember, 1 to 2 can take various paths, all right? But 2 to 1 is fixed. 2 to 1 is fixed. Okay? Now, let's play with this just a little bit more. Let me write my cyclic integral again, my Clausius inequality. So remember, del Q over T is equal to 0 for a reversible process and less than 0 for an irreversible process or cycle. Okay, so let's write the Clausius inequality one more time. Let's play the same game we did just a moment ago, but I'm going to let 1 to 2 be irreversible. I don't care what path it is, provided it's an irreversible path. So I'm just going to write here, irreversible. Let's just say these path 1 to 2, whatever that path is, now it's irreversible. Let's give that a shot. So let's write out the cyclic integral. Integral del Q over T. Again, that's going to be equal to the cyclic integral of del Q over T from 1 to 2 plus the cyclic integral of del Q over T. And remember, 2 to 1 is reversible. REV, reversible. 1 to 2, 2 to 1. Now, we've already hypothesized that del Q over T for a reversible process is equal to a change in a property, delta S. Now, this here is the integral of del Q over T from 2 to 1. So that means that this integral here is actually delta S from 2 to 1. Delta S from 2 to 1. Okay? All right? Now, because there are some irreversibilities in the cycle, the Clausius inequality says that the cyclic integral del Q over T over the cycle has got to be less than 0. Less than 0 because there are irreversibilities present in this process. Any path from 1 to 2, I'm telling you, is now irreversible. Okay? Now, I'm going to take delta S 2 to 1 and put it over on the other side of the inequality. So I get del Q over T integral from 1 to 2 is less than negative delta S from 2 to 1. The negative sign is because I'm taking it over on the other side of the equation, all right? Now this delta S from 2 to 1 is actually negative delta S from 2 to 1 is negative S1 minus S2. That's what delta S2 to 1 means, okay? If I distribute the negative sign, I get S2 minus S1, which is equal to delta S1 to 2. So this quantity here is actually equal to delta S1 to 2. Okay? Now I'm going to flip the equation and put the delta S change in entropy from state 1 to state 2. I'm going to put it on the other side of the inequality. I'm going to flip the whole inequality. Delta S 1 to 2 is greater than the integral of del Q over T 1 to 2. All right? And remember, this is for an irreversible process. That's for an irreversible process. Now let's look at what we just developed a moment ago. For a reversible process, delta S from 1 to 2 is equal to del Q over T for a reversible process. So let me write this equation right below what we've just developed. So we also have delta S from 1 to 2 is equal to the integral of del Q over T 1 to 2, provided 1 to 2 is a reversible process. So this quantity, delta S, is greater than this integral if it's an irreversible process and equal to the integral for greater than del Q integral of del Q over T for an irreversible process and equal to del Q over T integral of for a reversible process. This is what I'm going to do. I'm going to take this fact and I'm going to write out a new conservation equation for S. A brand new conservation or entropy balance for S. Delta S from 1 to 2 is equal to integral del Q over T plus S gen. Now, what is this S gen about? S gen, or S generated, is equal to 0 if the process is reversible, process 1 to 2, and greater than 0 for an irreversible process 1 to 2. What has happened here? What's this S gen about? Well, I've kind of tricked you a little bit. Let's go back to what we did here. Let's focus on these two equations right here. Basically, it says delta S from 1 to 2 is either equal to or greater than this integral depending on the process. And that's shown by this inequality right here, okay? The equality and the inequality. I've gotten rid of the inequality by swallowing it up into a brand new term called S gen. I've gotten rid of this inequality here. We don't want to work with inequalities. We want to work with equalities. That's what we're used to in mathematics and physics and engineering. So I got rid of the inequality. See here, delta S is equal to the integral of del Q over T plus S gen. I got rid of the inequality by swallowing it up into this S generated term, where S generated is 0 if it's a reversible process and positive if it is 0 if it's a reversible process and positive if it is a irreversible process. Okay? So, let's take a pause here. Okay, so let's write the entropy balance equation that we have over there. Let's write it and let's investigate what it is referring to. What does each term mean? So I have delta S from 1 to 2 is equal to the integral of del Q over T over the process 1 to 2 plus S generated from 1 to 2. All right? This is the entropy balance for a closed system. Now let's investigate what the terms mean. The first term is the easiest. The first term represents the change in entropy of the system as it moves from state 1 to state 2. So our system moves from state 1 to state 2. So delta S refers to the change in entropy of the system as we go from state 1 to state 2. System change in entropy S2 minus S1. So the system starts off with an entropy S1. And it goes to state 2 with an entropy of S2. That's what the first term means. It's your familiar delta E, delta P, delta T. Remember, we've hypothesized that entropy S is a property. So we're going to treat it like a property. S is a property, and delta S from state 1 to state 2 is S2 minus S1, okay? Where S is a property. The next term here, this guy, this represents the entropy transfer due to a heat interaction. S transfer due to heat transfer. Now the temperature T here, what temperature am I talking about? I'm going to put a little subscript right here, INT. I'm only going to do it for a little while. I'm going to leave it after a while. I'm going to drop it. I'll probably get sick of writing it. But what is this TINT? What is this temperature in the integral? Well, this is the interaction temperature. It's the temperature of the system at the point where the heat is transferred to the system. So if we have a system here and heat is getting transferred in, Q. So this is my system here. This is my system. If I stick a thermometer right there, the temperature at that point where the heat flows into the system is the interaction temperature. So T int equals, quote, interaction temperature. Interaction temperature. So temperature at the location where the heat is being transferred into the system. You stick a thermometer right there on the system boundary where the heat flows in. That is your interaction temperature. Okay? And then we have the third term here, our new term, the weird term. This represents entropy generation inside the system over the process due to irreversibilities. So this is S generated in system due to presence of irreversibility. So if there are irreversible processes within the system going on, unrestrained expansion, friction processes inside of our system, heat transfer across a finite temperature difference inside the system. That'll show up as an S-gen, positive S-gen in our entropy balance. Note, S-gen, remember, S-gen can either be 0 for a reversible process or positive for an irreversible process. Entropy can only be generated, it can't be consumed. So S-gen is always positive. Now, one thing I want to point out is we've derived this entropy balance here for a closed system overall process. We've derived it for a single heat interaction. So there's heat flowing into the system. This is our interaction temperature where the heat crosses the system boundary. And this integral is simply summing up the heat transfer over the temperature over the process. That's all it's doing. What if you have multiple heat transfers? We have Q coming in over here. We have Q coming in over here, or flowing out. You have all these interaction temperatures. T interaction, T interaction, all these interaction temperatures due to these various heat transfers. We've seen systems where there are multiple heat transfers, or certainly multiple heat transfers over time. So just in case there's more than one source of heat that we need to keep track of, I'm going to put a summation here. Why is the summation there? Because we may have multiple sources of heat flowing into or out of the system, okay? With that in mind, let us write the entropy balance in its full form and various versions. S balance, closed system. Let's make a little table here. You've seen this kind of stuff before. We have the basis, equation or expression. And then we have what? Units, S, I units, and English units. So, first of all, we have the entropy balance for an overall process. Overall process. That's going to be the equation we have written over there. Delta S from state 1 to state 2 is equal to the sum of the integral of del Q over the interaction temperature plus S gen from state 1 to state 2. Okay, that's a closed system entropy balance for an overall process. And we just discussed what these terms mean. Delta S is a change in entropy from state 1 to state 2. Del Q over T integrated, summed over all heat transfers. That's the entropy transfer due to heat flowing into the system. So heat brings entropy in or rejects entropy out of the system. And then we've got this S gen term. This is entropy generated within the system from state 1 to state 2 due to the presence of irreversibilities, okay? Now, what are the units on this? Well, the dimensions are, so we have the integral del Q over T. Del Q has units of energy and T has units of degrees. So the dimensions are energy per degree. So the SI unit would be what? A joule per Kelvin? Joule per degree Kelvin. Do not write joule per centigrade. Remember, all the second law stuff required temperature to be expressed in absolute terms. The temperature down there, the interaction temperature in the integral for the the transfer of entropy due to heat, that's got to be in absolute terms, okay? So a joule per Kelvin. English units, well, it can be a BTU per degree Rankine. That sounds good to me, per degree Rankine. And then we have the differential process, or infinitesimal differential. Differential process. So the delta becomes a d. ds is equal to the sum of del Q over the interaction temperature plus a little bit of S gen. Now I want to point out something here on the notation. There's a d here on the ds because S is a property. Entropy is a property. In fact, I'm going to write that right over here. Takeaway. Takeaways. Takeaways. S is a property. S is a property. So that's why it's got the D on here. S is a property or a point function. So the differential S is ds. The del Q, well, we already know that Q is a path function, so its differential transfer is del Q. We also know that S gen is path dependent. Why is it path dependent? Because S is positive for an irreversible process and 0 for a reversible process between the two same end states. So S gen is a path function. S gen is a path function, not a property, so it's got a del S gen there. Let's see, what about a rate-based? Rate-based. So I'm going to divide the differential process by dt, change in time, differential change in time, and I'm going to get a ds dt, which is S dot, if you like. I think I'll write that first. S dot. ds dt is equal to sum over multiple heat transfers, Q dot over the interaction temperature. So I divided the del Q by a dt. Del Q over dt is Q dot, heat per unit time. And then del S gen over dt becomes a S dot generated, the rate of heat of entropy generated due to irreversibility within the system. Okay? Oh, I guess we need the units here. For the differential process, it's still energy. So joule per degree Kelvin, and then I have BTU per degree Rankine. The rate-based, it's going to be the same thing as the overall process or the differential, but divided by time. So a joule per second is a watt. So I have a watt per degree Kelvin, and if you like, a horsepower per degree Rankine. Power or energy per unit time in English. I could also write the per unit mass overall process here, so everything would become a lowercase here on the overall process. So per unit mass, and I'll write overall. Everything's going to be lowercase here. So delta little s from 1 to 2, sum over all sources of heat, integral del little q over the interaction temperature plus little s gen from 1 to 2. Okay? Everything becomes lowercase if it's on a per unit mass basis. 4 different versions of the entropy balance. What's another thing that we can spot here is kind of interesting about this entropy balance? One thing is we haven't seen work for a little while. We haven't seen any W's. We have the energy balance, we have Q and W are both on the left-hand side of the equation. So the energy balance said heat and work were sort of similar or equivalent as far as the energy balance was concerned. I don't see any W's or work interactions going on in these entropy balance. The entropy balance doesn't care about the work. It only cares about heat transfer and S-gen. So what we can say here is entropy is transferred by heat, but not by work. So heat transfers energy and, I guess I'll write and entropy. So heat transfers energy, Q, and entropy, S. But work does not. Work does not transfer entropy. Work does not transfer entropy. Okay, let's do a little problem here. Let's take a pause for a moment. We'll get it set up. Okay, so what we have here is a wall. A wall, maybe it's in your house, who knows? We have some kind of a wall, a solid wall of some kind. Now, the temperature on the left side of the wall at location A, so TA, that is going to be 283 degrees Kelvin. So this is the outside of your house, and that's the inside of the house. So we have outside. Temperature outside is 283 degrees. So the temperature right here at the wall is 283 degrees, okay? 283 degrees. Now the temperature inside is equal to 298 degrees Kelvin. So you put a thermometer right there and you get 298 degrees, okay? Inside, outside temperature. Now it's warm inside, 298 versus 283. It's warm inside, so heat is going to spontaneously flow from the inside to the outside environment, okay? Going to flow from the inside of the house to the outside. So you got your Q dot, and Q dot is found to be equal to 1 kilowatt through the wall, all right? Now, what are we going to do here? We're going to take our wall as our control volume, our system. Our system is the wall. And we're going to calculate the quantity, Q dot over T at the outside surface, Q dot over T at the inside surface, and then we're going to calculate the entropy generation due to irreversibilities inside the wall. How do I know there's entropy being generated inside the wall? Well, what do you see going on here? You have an inside temperature of 298. You have an outside temperature of 283. There is a delta T between them. Heat flows from hot to cold over a finite delta T, or temperature difference. Is that a reversible or an irreversible process? The answer is the heat transfer through the wall is an irreversible process. So we're going to get an S dot gen in here due to irreversible heat transfer from hot to cold within the wall. So we're going to get an S dot gen in there. We're going to calculate that, all right? Okay, so let's go to the analysis. Let's calculate the quantity Q dot over T evaluated on the left-hand side of the wall. Q dot over T evaluate, and this is the interaction temperature, at the left-hand side of the wall, location A. Well, I know Q dot, and the temperature here, if I stick a thermometer right here at location A, right on the outside of the wall, I've got 283 degrees. So this is equal to Q dot over TA. Okay? Let's see here, Q dot over TA, that's 1 kilowatt divided by 283 degrees Kelvin. So 1 kilowatt divided by 283. And I get 3.5. I think I'll leave it, I'll write it in watts per Kelvin. Let's see here, 3.53 watts per degree Kelvin. I did the conversion from kilowatt into watts, okay? Let's calculate the quantity Q dot over T interaction on the right-hand side of the wall at location B. Now my interaction temperature, I stick a thermometer right here. My temperature right there on the surface is 298 degrees Kelvin or TB. So this is Q dot over TB, which is 1 kilowatt over 298 degrees Kelvin, okay? So 1 over 298. 3.35 watts per Kelvin. Watts per degree Kelvin, okay? So, on this side of the wall, so how do we interpret this result? What's going on here? Let's go back to the entropy balance. Let's go back to our entropy balances. We have a rate-based problem going on here. So I'm going to write the rate-based entropy balance and remind you what these terms mean. Rate-based S balance for a closed system. We have S dot equals the sum of Q dot over T interaction plus S dot gen. Okay? So what's the interpretation on these terms? Well, S dot is the rate of change of entropy within my system. Rate of S change in system is like the dECV dt or the dE dt in the energy balance, the change in energy over time. That's the rate of change in S within my system over time. This quantity here is the transfer of entropy due to a heat interaction. S transfer, or should I say rate of S transfer. Rate of S transfer due to heat interaction, okay? And then of course we've got the entropy generation here too. Rate of S generated due to irreversibility, okay? So this term here is entropy transfer due to a heat transfer. That means Q dot over T interaction at location B is an entropy transfer into the system due to a heat transfer. So I get S dot N, if you like, is equal to 3.35 watts per degree Kelvin. Okay? And S transfer out that's Q dot over T interaction at the left-hand side. That's 3.53 watts per degree Kelvin. Entropy is being transferred into the wall because heat's flowing into the wall, and entropy is being transferred out of the wall because then the heat flows out of the wall. By the way, I didn't say it here, and I think I better say it now. Let's assume this is a steady state problem. I'm going to insert this right up here. I forgot to write it. Steady state. Steady state. Okay, this is a steady state problem. So entropy flows in because of heat transfer, and entropy flows out because of heat transfer. Notice the outflow of entropy, 3.53, is greater than the inflow of entropy, 3.35 watts per degree Kelvin. Why the difference? Why is this entropy out transfer greater than the entropy in transfer? Because what's going on inside the wall? And what is going on inside the wall? Temperature is falling. So this is TA, and this is TB. A finite temperature difference. Finite temperature difference. Therefore, there's irreversibility is going on inside the wall, and that's resulting in entropy being generated. Let's calculate the entropy being generated in the wall. Let's go over here and apply the entropy balance to our wall. It's a rate-based problem, so I've got the rate-based entropy balance right over there. So I'll write it one more time. So S balance on wall system. S dot equals the sum of Q dot over T interaction plus S dot gen. Now, let's attack each term here in this entropy balance. S dot, that is ds dt in ds dt in the system or the wall. Change in entropy with respect to time in the wall. That's going to be 0 because it's a steady state problem. Steady state. Just like dE dt is 0 for a steady state problem, okay? What about these heat transfer terms? So here's my system right here. So I have Q dot over T at B, and I have Q dot over T interaction at A. This is my wall, and this is my system. Okay? So how many heat interactions do I have in this wall system? I've got 2. Some heat coming in, and then some heat leaving. That means I have 2 terms in here for my entropy transfer. I have the heat and the entropy flowing in from the left, so I have a Q dot over T B. So this guy is Q dot over TB. And then I have my entropy and energy flowing out on the left, and that is Q dot over TA. Let's write what I've got. 0 equals Q dot over TB minus Q dot over TA. Remember, the entropy is flowing in at B and flowing out at A. That's why there's a negative sign here. The heat transfer is in at B, so it's positive, and negative at the out left-hand side of the wall, which is location A. And then I've got my S dot generated. Let me solve for S dot generated. Let's calculate the rate of entropy generation within the wall. S dot gen equals Q dot over TA minus Q dot over TB. Now, I've already calculated these two terms here. Let's see here. Q dot over TA, that's 3.5 watts per degree Kelvin. 3.53, sorry. Watts per degree Kelvin minus the heat inflow, which is at location B, that's 3.35 watts per degree Kelvin, okay? And the difference is, well, I guess the difference is 0.18 watts per degree Kelvin, okay? 0.18 watt per degree Kelvin. So S dot gen, the rate of entropy generation within the wall is equal to 0.18 watts per degree Kelvin. So the S gen inside this wall, the difference between the inflow and the outflow of entropy, S dot gen, 0.18 watts per degree Kelvin, okay? So what's the source of this S gen? What's the source of this S gen? Why is it positive? This is telling us that there's irreversibilities going on within the wall, irreversible processes. What is the irreversible process? It's heat transfer across a finite temperature difference. So note, S dot gen is greater than 0 because we have irreversible heat transfer across a finite temperature difference. Irreversible heat transfer across a delta T. Irreversible heat transfer across a finite temperature difference delta T. By the way, what that means is the smaller this temperature difference gets, 298 versus 283, the smaller that temperature difference is between the left and the right-hand side of the wall, the lower the entropy generation within the wall. If these temperatures are nearly the same, this S gen will tend towards 0. And the limit, as TA and TB, the two walls have the same temperature, in the limit, S dot gen would go to 0. Okay, I think this is a good introduction, a good place to get your feet wet on entropy. We will do a bunch more examples next time.